Okay, so now we have the resistivity of the silicon, but the value is at room temperature. So this is the resistivity. Okay, so now first, write down your name and student ID. Based on this resistivity, calculate the resistance. To convince yourself the resistance is the value like this. So do the calculation based on the dimensions given here and the resistivity. Calculate the resistance. If you know the dimension and resistivity, then calculate the resistance. So, Marty, or sorry, your name again? Vipa. Vipa. Sorry, your name?
Muslim.
Muslim.
Yeah.
M-U-S-L-I-M?
Yeah.
Muslim. So the religion name?
Sorry?
Muslim is Christianity, Buddhism. Then.
That is the religious name, but he full name is Muslim Hussain.
Oh, okay. Vipa. Vipa.
Chinese name.
Chinese name. Okay, are you finished? So did you get the value here? Resistivity times length divided by cross-sectional area is the resistance. Now, given the coefficient of thermal expansion, TCR, TCR 5 to 10 to minus third Kelvin to minus 1. The thermal conductivity 0.7 watts per Kelvin centimeter. Now, calculate this thermal resistance, RTH. Can you go to the previous page? Previous. Okay, the equation for RTH is here. L divided by 8WH kappa. Kappa is the coefficient of thermal conductivity. And width, thickness, length. Okay, let's get back to our lecture. So you have calculated thermal resistance and thermal capacitance. Now we are ready to run the simulation. Okay, can you go to, so okay, now the thermal time constant multiply if you multiply these two values together, RTH times CTH, so time constant equal to RC for this thermal system. So if you make the multiplication, R times C, the result will be 0.1 millisecond. Okay, calculate. Please multiply RC to get this value. Okay, so the thermal time constant means if you turn your power on, after 0.1 millisecond, the system is ready to use. So it's very good, 0.1 millisecond. So if you have your poly resistor for heater, you should calculate this thermal time constant to know how quick your response is if you switch the power on. For a sensor, time constant should be long or short. Yeah, it should be short. Okay, good. Okay, next page. Then, if now let's know because this is a chemical sensor, we have the reaction gas come to contact with the sensor, then it will produce heat due to this chemical reaction. So the heat, remember, is power chemical reaction, PC. But at the beginning, we don't do the power from chemical reaction. We just want to see for our controller, if you set your point, say from 200 to 600, how good the controller will give you the resistance value. If you set the resistance 200, 250, or 350, then what's the real resistance you get from your system? So PC 0. So please go back to the MATLAB file. Yes, see, this is a setup. Beginning, PC equals 0. Then this is the KP value 1.6 for our controller. KP 0 equal to 1.6. Then VSATU 15 volt. Dimensions, resistivity, and reference temperature. We suppose our reference temperature, initial temperature, 0 degrees C. And Tm0 is the initial temperature of Tm. Can you go to Simulink? Simulink. Open the Simulink model. Double click. Yes. Okay, go to this filament subsystem. So this is Tm dot dTm dt and integration equal Tm. So can you double click this integrator? So see, this is the integrator. We have the initial condition for this integration. So initial condition is Tm0. So you need to put your Tm0 here. The default is 0. But if you have different initial condition, you can set up your initial condition here, Tm0. Okay, close this one. Go back to PPT. So we go back to, yes. Then we have we calculate this initial value R, 200 ohm. Then we have temperature coefficient of resistance. So it is positive value. Temperature coefficient of resistance. So if it is positive, means let me ask, Frank, if the temperature coefficient of resistance is positive, means temperature increase, what happened to the resistance? Yes, increase. So you can imagine RT equal to R0 times parentheses 1 plus TCR times delta T. So TCR is the temperature coefficient of resistance. Then kappa is the thermal conductivity. This is the C tilde, room temperature specific heat. Then we have density of silicon. Because we need density to calculate the C tilde from C heat. Then we have thermal resistance. We have thermal capacitance. But in this case, remember, the real time constant is 0.1 millisecond. It is too short. And in this case, they assume the time constant is 1 second. So because they want to say the time constant should be 1, so they assume thermal capacitance equal to 1 divided by thermal resistance. In this case, thermal resistance times thermal capacitance will be 1. So just artificially, we increase the time constant. Okay, so now we do the simulation. Because this is a differential equation, we need to have the initial time 0, and stop time, the final time. So we do the simulation. You don't need to do anything. 1.4 times thermal time constant. Now the thermal time constant is 1. So stop time is 1.4. Multiply that, so it's 1.4 second, final time. And this is time increment. So the time increment should be small in order to catch the response of your Simulink simulation. Usually it should be 1,000th or even like 1 millionth, depends on your case. You can keep decrease your time constant until you find out if you decrease your time constant, the response won't change anymore. In that case, you know you have the correct time constant. So do you understand this point? Okay. So initial, I could take 0.01, then I decrease 0.001 till the response won't change anymore. Then I know the suitable time constant, time increment to use. Okay, then because I want to go to the PPT, because I want to have the set point from 200 to 600, so I need to run each case. Run this case, get the response. Run this case, get response. Run this case to get the response. So I create a for loop to run several cases. And in order to create the curve, go to the MATLAB file. Okay, so I use for loop for set point from 200 to 600. Each time I increase 10. So this is the for loop. So for each loop, I run the simulation, Simulink simulation, SIM, is a command to link to the Simulink. So SIM, then quote, MDL name. MDL, go to the file directory. So MDL is the old version of the Simulink file. The new, if you use new, like after 2018, MATLAB changed the MDL file name to SLX. SLX. So SLX is the new version of MDL file. Okay, go back to file. Yes. Okay, so this is the name of the MDL or SLX file you created in Simulink. Then this is time t here. The time, the vector of time vector here. So you will run Simulink, and your output you have. So you must have this t time and x. X is the state variable. You must have t and x. After that, you can have your output. So output E1, 2, 3, 4. Can you go back to the Simulink? Go back to, yes, this one. See, you create output, voltage, output 1, temp, output 2. power output 3, and resistance output 4. So, sorry, 4 here. So 1, 2, 3, 4. You have 4 outputs. Okay, go back to the file. See, you have voltage, temp, power, resistance. You have 4 outputs. Then every time you run this, the set point, then you want to save the value. You want to save this voltage, because now voltage is an array from time 0 to stop time. So we just need the final value of this voltage array. So we take the final value and save it to VOL/FRN to a new array. And this is count. So count equal to 1. For each for loop, count equal to count plus 1. So this array will save the final value of voltage in each set point. If you understand, raise your hand. Okay, very good. Then we save the final value of TEMP, power, and resistance to these arrays. Then scroll down. Scroll down. Okay, we want to plot. Go back to PPT. See, you want to plot the resistance versus set point. Okay, so go to the, yes. So we want to plot. So the x coordinate is set point. Y coordinate is final resistance. So we have this one. And we use this is the curve color. This is this is not dotted, yet not solid. One solid, one dot, solid dot, solid dot. So this is the line type you will use. And figure 1. Then we give this plot a handle, means the plot. And you can think this is a pointer, point to your figure. So we set this target, the line width. The line width is 1. So you can, if you want the thicker line, you can change the line width. Then we want to can you go to the PPT? Next page. Next page. Next. Sorry, can you go back to this page? Go back to this page, yes. So we set the line width of the curve, but we also want to have beautiful, very journal paper quality, the X number and Y coordinate number. So in order to have better quality of this X number and Y coordinate number, go to this one. You need to set GCA, current figure, the line width, LW, font size, the size of the label, FS label. See, FS label 16. The label means the font size label. This way you can have high quality of your figure, and the journal office would prefer beautiful figures. So it's important, if you are ready to publish your paper, it's better you have this paper figure quality. Okay, then the X label set point. And if you have this forward slash omega, you will create the, okay, can you go to the PPT? See, in this, you use OHMS, but it would be good if you use the Greek omega as the unit for ohm. So omega is this one. So it's a symbol for ohm. Can you go to this file? And if this is the lowercase, it's omega like this. If you use uppercase, then it is the capital omega in Greek later. Okay? So this is set point and resistance omega ohm. And from size, we increase the size of X label. We increase the size of Y label. Okay. And also we have this command. We calculate slope. Slope is the Y coordinate divided by the X coordinate. The final value of set point divided minus the initial value. The final value of Y coordinate minus the initial value of Y coordinate. This way you will calculate the slope of the curve. But we want to put this slope. Can you go to this PowerPoint, PPT? We want to put this on your figure. So go back to this one. Slope is a number. We need to this is a converter. We convert number to string. So we convert this number to a string, and we save this string to this string variable. But can you go to this PPT? For me, I want to create this, and I want to have an arrow pointed to this curve. So can you go to this? Then this next forward slash left arrow means I create an arrow. Then string catenation means I connect this string with this string. This string connect this string and put two stream, combine two stream together. So this is the command strcat, string catenation. So str1 is the stream. So finally, I want to put this text on the figure. I use the command text. So str1 is the stream. I do change it to a cell stream. Then I put this one into this location. This is the X coordinate, and this is the Y coordinate on the figure. So set point length divided by 2 and round. And set point length divided by 2. Round means I just take the integer. I remove all the digits after the integer. So the reason is, can you go back to this? To go back to this one. Sorry, go back to figure 1. Figure 1. Yes. See, this is left arrow slope. So this is number to string. So I put these two string Then, but this stream, we need to know the x and y coordinate. Because this one you could put it anywhere, but you need to know the x coordinate and y coordinate of this line. So I select the center point. So the center point, this is 200, 600, 200, 600. So can you go back to this? Can you move? Yeah, okay. See, set point is an array. 阿明，你睡着了。Set point is an array, 200 to 600. Can you go up? Go up. See, set point is an array with the number of elements count. Okay, scroll down. So set point, this array, length array means the element number, how many elements in this array. So this is the number of elements divided by 2. But this is an integer divided by an integer. Maybe it's not an integer. Maybe it has some digits after the integer. So we take round to remove all digits after the integer. So this would be an integer. And because for an array it has many elements, I want to select the center elements. So I need to know the location of this element in this array. But this location must be an integer. It cannot be any number with the digits. So that's why I use round. Then, so this is the location near the center of set point. And this is the location near the center of y coordinate. So this way I could create the text at this location with this cell string str1. So that's why I created figure 1 here. So figure 1 looks like this. If you don't do this, the result would be, okay, can you go back to figure 1? Can you comment this? Yeah, comment this comment. Comment. Percent, put a percent at the beginning. And this one. And this one. And this one. This one. And this one. And remove the font size ABS label. Yeah, remove, yes. Yes. And remove this one. Okay, then remove R. Remove this one. Yes. And okay. Okay, save it. Okay, then run the file again. Okay, go to figure 1. So this is a figure without all those editing. So you could see the size of the numbers are small compared to the figure like this one. So for a journal paper, if your figure looks like this, the editor may just reject your paper, maybe, because it doesn't look good. It just looks like very basic figures. And for readers, if you read a journal paper, the figures in the journal paper, you have the figure, the size. It's very clear for the reviewers to see clearly the numbers, the figures. If the figure look like this, if I am the reviewer, I may give a low point to this paper. If the reviewer gives low points to your paper might be rejected by the general editor. So it's your choice. You do your research, you spend a lot of time. But if you don't finish the final mile to do the editing of your results, those people may not appreciate your hard work. I mean, do you understand? Okay. Stephen, do you get it? Okay, are you going to publish any paper? Okay. Okay, so let's go back to PPT. See, full view. See, our controller is pretty good. The slope, the perfect case, Frank, our intention is the perfect value of the slope should be, what should be the slope be? What is the slope, the best case? Do you want the set point resistance and the final resistance to be equal to each other? Would you like that? I set the T value to be 100. Then your controller will try to reach the goal. Try very hard. So the best case is they should be the same, right? So if they should be the same, what is the slope? Should be 1. Okay. So in this case, we use a controller, is KP controller, proportional controller, without integrator or differentiator. So for this simple controller, the slope is 0.993, very close to 1. So it means our controller is good enough. Okay, but in it now, because we don't have PC, there's no chemical reaction. So it's very simple case, just to test your system. Initial test. Let's say test 1, we pass. Now we need to test more complicated scenario. Okay, next page. So now, for PC equal to 0, we can create a figure of the power at set point versus temperature rise. So if you set the temperature to be 3, you set the T to be 350 ohm, then you need to have voltage, power input to your system to increase the temperature of your resistance, to increase the resistance. So this is power input and the temperature rise. So in this figure, we have left y coordinate and right y coordinate. And right y coordinate represent the voltage you used. You tell your controller, your circuit, this is the voltage you need. And this is the temperature rise. If you have higher voltage, you have higher temperature rise. Okay, can you go back to the Yes, figure 3. See, for figure 3, you have y-axis left for the temperature rise. And for this figure 3, you have y-axis right. Scroll down. So for y-axis right, you have voltage. So in this figure, you have two y-coordinates. So which is good enough to present your result. So for my students, because your advisor is me, so can you go back to MATLAB? So in the future, if you present your result to me, you report your result, please use this template, this file as your template to show your figures in your PPT file. Okay? Yes, let's go back to PPT. Okay, now we want to make the story more exciting. So now the PC is no longer 0. We put our sensor to a gas chamber to sense the gas. Okay, next page. Now the PC, we have PC value. Initially 0. But now we increase the PC. So if you increase the PC, the power, because remember we want to keep the temperature at the same temperature, then power from your circuit and power from your chemical reaction. If your chemical reaction power increase, then your power from your circuit should decrease in order to keep your polysilicon sensor at the same temperature. If you don't change your power input, then the chemical reaction power will increase your temperature of your sensor, your resistor. So in order to keep your resistor has the same temperature, if you have chemical reaction, then you need to decrease your power input to your circuit. Okay, so Muslim, could you read this? Yeah, read.
This sensor can only function as a sensor as opposed to a combustion catalyst when PC is less than the steady state power required at the set point temperature.
Okay, thank you. So in the future, you don't need to stand up. You can just sit and to answer the question. See, in this simulation, you know if the chemical reaction power is higher than 0.022, then the power input from circuit will go to negative, so which is impossible. So the capacity of your sensor, the maximum is 0.022 watts for the power from the chemical reaction, because it's impossible for you to have power from your circuit to be negative. Okay? Then this slope minus 0.993 should be closed. Can you go to previous? Previous. Should be the same as this slope. The set point resistance slope. Okay. Can you go back to the MATLAB? Okay. Sorry, go to the PPT again. So for this figure is Can you go to the file directory? And 23.2 figure 23.878. Can you open this MATLAB file with text editor? Can you this is PC. Okay. So in this file, I have this for loop for PC from 0 to 0.022. And I run the Simulink to get the voltage, temperature, power, resistance. Okay. Scroll down. So I plot the figure. Now you should be able to read this MATLAB file by yourself. I will ask Ethan. Yeah. What is the function of this command? This one.
Slope.
Okay, slope. Yes. But what is this function? The function of this command. Sorry. BPA. What's the function of this command? Yeah. To convert number to string. Number to string. Okay. Ahwan, what's the function of this command? strcat. Okay, Amin, what's the function of this one? Kumel, what's the function of this one?
Yeah, string 1 and string 2 gets back.
Okay, good. Frank, what's the function of this one? Text. What's the purpose of this command? Okay, Lai, what's the purpose of this command?
Make all the text in the figure around in the center of the figure.
Okay. So, in this round of questioning, BPAP, Kumel, Lai, Vietnam, Kashmir, India, totally win over Taiwanese students. Okay, can you go back to PPT? Okay, so we created the figures. Okay, next page. Next. Okay, next. Now, previous figures, we have steady state result. Remember, we have time constant. The system responds to your input. It takes some time to reach steady state result, stable result. And now we are interested in knowing the transient response before we reach the final steady state. Okay, so now we are going to do that. Botan, what is steady state result? You can explain, use a lot, some other sentences.
Instead is increase some, for example, set up 100 steps and one time increase one and go to 100 and look the result.
Okay. Sorry, what's your name?
Yeah.
Leo. So what is transient response? Transient. Transient 是站态响应 ，steady state 是稳态响应。哈？
在讲英文。
哈
在讲英文吗？
？It's up to you.
全学上就是还没到稳态之前的那个，就到稳态之后，它会维持在一个区间里面。
Yes.
然后站态的时候，它是就一个过程。
Okay. All right. Okay, now we want to know the transient response of our system. So in this figure, we input our PC. Remember, PC is a chemical reaction power. So this is the input. Input is the square wave of the PC watts. Under this condition, what's the response of our system in terms of time? So x coordinate represent the time, and left y represent chemical power, and right y represent the power from your power source, your power supply. Okay. So Leo, could you read this?
Calculating these transistors, it was necessary to reduce the relative tolerance in simulating a value of 1e-6 was used. If the default value of 1e-3 is used, numerical instabilities can result from step changes.
Okay, good. Thank you. Now, English time. How to read this in English? 10 to minus 6. So 10 is this number. 10, 2. 2 go up. Minus is this minus sign. And this one, 6, th. Remember to add th. So this is 10 to minus 6. So this one is 10 to minus 6. So, Stephen, use English to read this. Huh? Louder. Okay. All right. In previous version of MATLAB, we need to set the tolerance to Simulink. But for the new version of MATLAB, you are not required to do that. It will automatically do this for you. Okay, let's go to file 23_8. The file directory. 23.8, yeah, _8. Okay, now we have a square power input. Then this is we want to keep our TM 468.8 ohm. So this is the set point. And KP 1.6, V saturation, 15 volt, dimension, resistivity, initial temperature of the sensor resistor, initial resistance, temperature coefficient of resistance, thermal conductivity, thermal resistance. In order to have time constant equal to 1, we set thermal capacitance equal to 1 over RTH. So in English, we read 1 over RTH. Ami, could you use English to read this?
1 divided RTH.
波成
1 over RTH.
1 over means higher than something. Over, below, lower than something. Over means higher, over the sky. Okay, scroll down. Scroll up. We want to create the square wave for the input. For this square wave, we need to have the amplitude of the square wave and the period of the square wave. Can you go back to the PPT? See, this is the input signal. So from this input signal, Ahwan, what's the period of the input signal? Period. Do you know what period is? Yes. Okay, what's the period of this input signal? Okay, 0.2, because this is one period, one cycle. So this is the period, 1.1 minus 0.9. And this is the amplitude of this square wave, 0.01 watts. Can you go back to the, yes. So see, 0.01, this is the amplitude. And the period, 0.2. Because thermal time constant is 1. Anyway, so 0.2 times 1 equal to 0.2. And the pulse width 50%. So this is unit of this one is percent, because the duty cycle of this square wave is 50%. So Muslim, do you know what duty cycle is?
Repetition.
Okay, can you go back to PPT? Okay, for this is one cycle. For this cycle, we have signal high, signal low. This high signal occupies 50% of this period. So the duty cycle is 50%. So this is duty cycle. Okay, go back to editor. 50% of the period is the pulse width, means, okay, duty cycle. And pulse delay, can you go back to the PPT? See, for this cycle, the signal is not on in the beginning. It delays this time to be on. So this is the delay of the signal. Okay, go back to, so the pulse delay. Wait, pulse delay is 0. Can you go back to the, sorry, so this is 0.9, 1.4. So if you go back to time 0, so this is 0.5. So if you plot this one to 0, the signal is on at the beginning. So 0 on, then 0.1 low, 0.2 on, 0.3 low. Okay, sorry, so this is 0.9. So, okay, can you go back? So the pulse delay is 0, means it's on at the beginning. Then the stop time now is 1.4 seconds. So I decrease this time increment because now we are interested in Leo. Now we are interested in transient response or steady state result. Which one we are interested in? BPOP. Which one we are interested in now? Transient or steady state? Transient. Because we want to know the transient response, we need to decrease the time increment in order to know the transient response before it reach the steady state. Okay, so I decrease the time increment. Okay, scroll down. Then I run the Simulink to get the, so we have time. So t is the time vector. So you have time. So we plot x coordinate time, and y coordinate is the power of your circuit, your power supply. So PC, P, go back. Yeah, this is the power, PC, power supply. Sorry, PC is the chemical reaction. So this is the input signal. Then scroll down. So X label is time, and Y label is the PC, the signal input. So this is Y, left Y-axis. The right Y-axis is power supply, and this is time. Okay, so can you run this 23_8? Yes. Okay, so this is the result. See, this is the style, figure style I prefer. Bigger font size. and very clear, and different color of your curve, a different line type of your curve. So this way, people, your reader, the reader of your paper the figure is very clear to your readers. The line we have certain thickness. It's not too thin. And the color is very clear. And the line type, it's important to have different line types. Because when people use Xerox machine, do you know what Xerox is? Xerox is 正蛋行 the English name of. So Xerox, in long time ago, Xerox is the world #1 manufacturer of the photocopy machine. So in United States, they use Xerox, the company name, to mean photocopier. So when we say Xerox, we use that name as the photocopy. Okay, so if I get the PDF file, on the computer screen, you have different colors. So it's very easy for you to know, okay, red color, so this one goes to this one. This one, solid. Black goes to this one. But usually we don't use color printing. We use black and white printing. So if you use black and white, there's no way you have color output. So it's better you use different line type. Then if I read the paper, then it's easy for me to know the difference of the two curves. If I use the same solid line and solid line, just different color, then it won't be. It's not easy for me to tell the difference of your result. Okay. So that's why MATLAB is a very powerful tool, not only for numerical calculation, but to present, to show your result, to create very beautiful result. So okay, so this is the reason why I want to use very small time increment, 0.001. If I use large increment, I won't be able to see this transient response. If I use large increment, I will only see this one. So the result will be like this. So you will miss the transient response of your system behavior. So that's why we need to select small time increment. And you can have this point. Okay, so go back to PPT. Okay, next page. Ahwan, could you read this?
There is almost one-to-one match between the data increase in PC and the rapid increase in jar hits out.
Okay, this is a power output power. So if the PC, you have chemical reaction, your sensor detects the gas in the chamber. So this is the power of chemical reaction. As long as this chemical reaction occurs, your power supply power is going to drop. So this go up, go down, go down, go up, go up, go down, go down, go up. So there's one-to-one correspondence between your input and your output. Next page. Now, for Simulink, we can just say we have KP, and it's a proportional controller. But for electrical engineer, they need to realize this controller using circuit. So for electrical engineer, they need to use OP and all this circuit block to create this 1.6 controller. So this is the OP, and the filament is the resistor in your system. So this is MEMS resistance. So for mechanical engineer, we do this part only. For electrical engineer, they do all the others. So that's why electrical engineer get high salary. Mechanical engineer get low salary. Because your contribution on a chip, say a die, 1.5 millimeter times 1.5 millimeter. The MEMS sensor part may occupy 1 millimeter times 1 millimeter. And the circuit, very small, might occupy only 0.5 millimeter times 0.5 millimeter. But it's more complicated. The circuit is kind of easier for the mechanical part. So this is the reality. So that's why you are valuable in the world, electrical engineer. Okay, this is the power supply, 15 volt to this circuit. Okay, Botan, could you read this?
Two differential amplifiers measure the voltage across the filament and 10 times the current shown in.
Okay, so this is a differential OP. And we have this current goes through, and we have this is voltage. So yeah, 10 times the current through it. So the current goes and multiplied by this, we can get voltage. And you use FET for the power supply, the source. Okay, so the purpose of this is to create the proportional controller, KP. Next. Then, Ami, could you read the first point?
The outputs are divided in an analog device 80 by 3 volt analog device. The result is the voltage drop proportional to the filament resistor. The set point voltage is then applied.
Okay, through this analog divider, then we have the signal compared to the set point. So we use this OP to compare this value, set point, and this feedback signal. Okay, then Kumail, could you read this? Second.
The voltage at the source of the FET is approximately one threshold voltage below the output of the 1000 amplifier. The combined effect of the three amplifiers and the analog division is a factor of 1.6, which is what was used in the resistance control system.
Yes. See, this is the resistor. So this is the drain. This is the source. So the drain voltage is 1 VT lower than this gate source. Then we can make sure this resistor can function in the region we want. So, Frank, do you understand this transistor? OP? You are confused. It's okay. Yeah, you just need to know the circuit. This circuit will create this resistance control 1.6, this factor, Kp. For the detail, you can study the analog circuit design. You can go to the electrical engineering department to select the course. You'll be excited. Okay, next page. Okay, the fabrication part. Okay, I will have Bo-Cheng, could you read the first one?
It's about to have a low resistive material for the filament, which used for either a metal or heavy top polysilicon.
Okay, so for the filament is a resistor. If we have low resistivity, because the power dissipation equal to low resistivity. Sorry. The thermal expansion part, because for any structure, if we increase the temperature, it's going to expand. But we prefer the dimension of the resistor to stay the same. So we prefer low resistivity to avoid the thermal expansion. Sorry. We select polysilicon because it has low coefficient of thermal expansion. Then it won't expand too much if the temperature is high. So that's why we select polysilicon. The other thing is for CMOS process, polysilicon is very common. Then it's very cheap to produce polysilicon in the CMOS technology. So we select polysilicon. And for the polysilicon, if you metal plus polysilicon is silicide, means we add metal to the polysilicon to lower the resistivity of the polysilicon. Or we use doping. We put a lot of dopants like to the polysilicon to increase its conductivity. Okay, then Bipa, could you read the third point? Yeah.
Thermal expansion coefficient of a silicon substrate is 2.5 E2 minus 6, but
Oh, sorry, could you read 2.5? 10 to minus 6.
E2 minus 6. Or
Per K,
okay.
PER,
Yes.
per K.
Okay. If a metal such as tungsten is used for the filament with a thermal expansion coefficient of 4.5 10 to minus 6 per K.
Yes, see, for silicon, is low thermal coefficient expansion, 2.5 10 to minus 6 per K. But for tungsten, it's relatively high, metal has high coefficient of thermal expansion. Okay, Martin, could you read this?
Because platinum reacts with silicon at elevated temperatures to form a silicide, and because the presence of conducting platinum would alter the electrical power dissipation pattern, it was decided to insulate the filament from the catalyst with a thin silicon nitride film.
Okay, we have the film, the polysilicon resistor. But this polysilicon is going to react with platinum because the platinum is the catalyst to speed up the chemical reaction between hydrogen and the oxygen. Because this gas sensor is hydrogen gas sensor. So the hydrogen is going to react with oxygen. Then we have combustion reaction to produce heat. So, but if the platinum, the catalyst, contact the polysilicon, they will have reaction. Metal plus polysilicon, we have silicide. So the silicide will change the resistivity of the polysilicon. So we don't want the catalyst platinum to directly contact the polysilicon. So we need to have an interface layer between the catalyst platinum and the polysilicon. And this insulator should have low. Insulator means it's not a conductor. So we select silicon nitride. So on polysilicon, we deposit silicon nitride. Silicon nitride is an insulator to avoid the direct contact between the platinum and polysilicon. Okay. So come back to this low resistivity. Remember, the resistor is a heater. So the joule heat equal to voltage square over resistance. So we prefer low resistance to have high joule heat output. Do you get it? So low resistivity is desired. So low resistivity is desired. But for low resistivity, either we use metal or use polysilicon. But we select polysilicon because it's very cheap to have polysilicon in the CMOS process. And it has low thermal expansion. Metal has high coefficient of thermal expansion. Okay, next page. Okay, so we have poly. So we have this oxide. Then on oxide, we have polysilicon. At polysilicon, we have nitride to separate the platinum and the polysilicon. So we remove the oxide. Then we have this one after release. So this is the SEM, the electronic photo, the SEM photo. So this is the filament. This is the filament. We have anchor. We have pad here, pad. So the filament is very thin. Okay, to have low resistivity. Because resistance equal to rho L divided by A. L is length, A is the cross-sectional area. So low cross-sectional area Sorry, I made a mistake. So it has nothing to do with rho L divided by A. Sorry. Next page. So we have coat platinum on this filament. So you pad. And this is wire bonding. Okay, Bolton, could you read this?
Pattern
Okay, acetonate
will decompose at temperature above 350 degrees C by operating at filament at less temperature in a gas cell to which PTACAC vapor is support selective chemical vapor deposition can be achieved.
So this is, okay, thank you. This is a process to deposit platinum on the filament. So we have this raw material, PTACAC. So it's an organic metallic material. Then we can increase the temperature to turn the PTACAC to be vapor. So the temperature higher than 350 degrees C, this organoplatinum will decompose to generate PT. Then the PT vapor will drop on the filament to deposit the PT on the filament. So this is catalyst coating process. Next page. So hydrogen detection. So this is a gas sensor to detect hydrogen. So this X coordinate represent time. And so now we start the experiment. We go to the gas chamber. We open the gas input. So the gas in. Sorry. This is sensor response. So this is gas, 1.6% hydrogen. So you have voltage output. Now we close the chamber. Now there's no hydrogen. So the voltage goes back to the ordinary value. Now we let in the 1% hydrogen gas. So the voltage output comes to this value. So you see this 1-to-1 correspondence between voltage value and the concentration of hydrogen. So we use this experiment to show this is our gas sensor. By reading the voltage output, it will know the concentration of hydrogen gas.